The topic of today's lecture is interference, and the following few lectures also I will be talking about the different aspects of interference. Okay. I feel this is a very important important chapter in all of laser course, because it occurs in some form or the other in different parts of the course. And I won't have spoken specifically on interference, but I want to do so now, so that if you know the basic principles of interference, it can be applied to many of the optics and or optical systems that are used in, say, a laser laboratory or any experimental system that deals with lasers. Though interference is not as though it was discovered after after the lasers were invented. It was there much before that. You can get interference with ordinary light around, but there are some specific conditions that have to be followed in order to see an interference pattern. Okay. So, we want to study today what are those specific parameters that are required for any light in order to show a interference pattern, okay, or to show the interference phenomena itself. Okay. So, let us start with the basic idea. So, the basic idea is that intensity of a wave resulting from the superposition of two or more waves is determined by the relation between their phases and polarizations. Okay. So, here it is, and then there is a formal definition. All of you of course know what interference means, what interference fringes are, but let me go through the formal definition. Okay. So, the formal definition is interference is the change in average energy flux density caused by the superposition of electromagnetic waves. Energy flux density are proportional to the square of the amplitude of the electromagnetic wave, and the proportionality factors are constant for a given medium. Okay. This you have come across at different parts of the lectures that I have given previously. This is X here. Okay. So, so here this is just a formal description. So, consider for the moment a monochromatic wave. Okay. Monochromatic is the key to getting an interference pattern. Consider a monochromatic wave. I am not saying anything about lasers. This is any general light. So, all these derivations that we will go through is for any general light, and I is the intensity and E0 is the amplitude of the wave. Okay. So, I generally we know to get the intensity we take the square of the amplitude. Okay. So, this is the amplitude. So, intensity I will be given as real part of E, as you know, has a imaginary part also, the electric field or electric wave that is associated with that light. Okay. So, real part and real part of E, you take the average of that. Okay. And it can be written as half of real part of E star E. So, the moment you take E star E, I suppose one need not write real here, I mean the imaginary parts just go away. Okay. In any case, to be exact, I have said real part of E star E, which is equal to half E0 square. If both these waves, there is just one wave that I am talking about, and E0 is the amplitude of the wave E. Now, two waves that are linearly polarized, I will consider that, in the same direction and have identical amplitude can be represented as follows. You are familiar with this. This is a travelling wave going in, say, the x direction. So, it can be written as e to in terms of either sine or cos, or in short in terms of this exponential factor, e to the power minus I omega t minus phi 1. Okay. So, this is the phase which is related to the first wave, which is E1, and E0 happens to be its amplitude. Okay. And omega is the frequency. There is only one frequency, because I have said it is monochromatic. Okay. So, we will strictly adhere to that it is monochromatic. But for the second wave, it has the same amplitude as the first. There are two waves, first and the second. So, we want to see what is the interference between these two waves, and each of them have the same frequency or the same wavelength, and they are monochromatic. Okay. And this is, but they differ in, there is a difference in their phase. This is this phi 2. Okay. This term shows it is travelling in time. Phi 2 is the phase of this E2, and phi 1 is the phase of E1. Okay. So, these are the two waves. Now, let us see what will happen if they interfere. By interfering means we are superposing one beam on top of the other, or both of them are crossing paths, and they are crossing paths in time and also in space. Okay. These two have to be, it is not that one has gone past and then the next one comes, no, you will not get an interference pattern. So, in space and time, these two waves are superposing on each other. Okay. And what happens because of the superposition? So, superposition, as we have seen even before, is it's kind of the addition of these two waves. And I have added this, and then suppose I go to the intensity. I just follow this formula here. Intensity will be half real of E1 star, which is here, E1 star plus E2 star, that is the total E, because now there are two waves, E1 plus E2. I have already got it as E. E1 star plus E2 star into E1 plus E2. Okay. So, that corresponds to E star E here. Okay. This is what I have. So, half of, I just open up, E1 star E1 plus E2 star E2 plus E1 star E2 plus E2 star E1. Okay. So, now what is each of these? E1 star E, E1 star E here. So, if you were to take E1 star E, your I will disappear in any case. Okay. This part will become 1. So, you have E1 star E is equal to E0 square. Similarly, E2 star E will be this multiplied by the complex conjugate of this. Okay. Complex conjugate means I have a plus I here. Okay. So, this part becomes 1. Okay. So, E2 star E2 is E0 square. Okay. So, E1 star E1 is also is E0 2 square, and E2 star E2 is also E0 square. So, that is square of the amplitude there. Now, what about E1 star E2? E1 star E2 will be E1 star, the star of this E2. It will E0 square, and I will have this term. Okay. So, if I suppose I have written it like this, E1 star E2, I am just writing it down so that you are absolutely clear about what is being done, though you know what is being done. So, I have a term e to the power minus I omega t minus phi 1 multiplied by e to the power, complex conjugate is here. So, I have another term plus I into this term in bracket. Okay. So, the only omega t will cancel out with the omega t here, only phi 1 and phi 2 will remain, and that is what I have got here. Okay. Phi 1 and phi 2 has remained. Then similarly for E2 star E, I will have E0 square. This is the initial amplitude square, and then again a similar term. So, this is with a plus I and this is with a minus I, just note that. Okay. So, what will be my intensity? Intensity will be this, I will just plug all these things in here in this equation. I just push in all these equations here, and it works out to be E0 square 1 plus cos delta. Okay. Cos delta, because I have just expanded this by the Euler's equation and identity, which is e to the power I theta can be written in terms of cos and sine. Okay. So, it will be cos of that plus sine of the other. Okay. So, e to the power I theta can be written as that. So, that is what I have done. I have just written this term and this term in terms of cos and sine, and the sine term cancels out, and you are just left over by the cos term. And delta is equal to phi 2 minus phi 1. This part is delta. Okay. So, E0 square 1 plus cos delta. So, the intensity is I0. I am just calling E0 square as I0 now. Okay. Plus 1 plus cos delta. So, this is called the interference formula. Delta is equal to phi 2 minus phi 1, and I0 is the intensity of the initial wave. Okay. So, this interference formula is very important. If you can see, the interference is dependent on the phase of the two waves, nothing else. It is just dependent on the phase, okay? This phase, phi 2 minus phi 1. So, it depends on the phase of the phase of one of the waves and phase of the other wave, or one can say the difference in phase of the two waves. Okay. So, the intensity pattern itself depends on this phase. Okay. So, phase is not something which you are going to actually see on a screen or see on your detector. You will see the intensity pattern, but the intensity pattern will follow the instructions of the phase. As you can see in this formula, I is equal to I0 1 plus cos delta. Okay. So, let us see how they will follow it. So, here before I go on to how it will follow the interference pattern, let me see, I is equal to I0 1 plus cos delta. I will just write it here for reference. I equal to I0 1 plus cos of delta. Okay, just keep it aside, just remember, keep this at the back of your mind. Okay. Now, what I do is, I am continuing with the interference derivation of two waves, but what I will consider is a more generalized case when the waves have different amplitudes. See, till now I took the amplitude as E0. E1 and E2 both started initially with an amplitude of E0. Okay. But it may not happen that way always. Can you really get a interference pattern even when you do not have that amplitude which are equal? That is why I consider a generalized case where I start off with the wave same as before, but here the amplitude is E01. The first wave has amplitude E01 and the second one E02. Okay. So, this is equal to E2. E2 is equal to okay. So, E2 is equal to E02. So now then what will happen to E1 E1 star E1 will be E01 square, E2 star E2 will be E02 02 square. That means it is square of their individual amplitudes, okay, 01 and 02 amplitude. Okay. Then E1 star E2 is equal to E01 E02. Okay. E to the power I phi 2 minus phi 1. Okay, that you can see. You just multiply these two and this is what you will get. And E2 star E1 will also be E20 E01. So, this part of this amplitude part is multiplication of the two amplitudes, but they are different. E to the power I phi 2 minus phi 1. Okay. So, this is what I get. Now, again I plug it into the intensity formula. Then intensity I is half E01 square plus E02 square plus 2 E01 E02 cos delta. Delta is again the same, phi 2 minus phi 1. That means the difference in phase between the two waves. So, all I have done this time is change the amplitude of the two waves, nothing else. Okay. The phase has remained, each of them have their own phases. Okay. So, if I write E01 as I1 and E02 square, sorry, E01 square as I1 and E02 square as I2. Okay. That is, I have started with the initial intensity of the two beams of light, okay, as I1 and I2, plus 2 of root of I1, because this will be root. Okay. E01 square is I1, so only E01 will be root of that. Root of I1, root of I2 cos delta. So, all I have done is just plug in all these formula into the intensity thing. Now, this intensity formula has a slightly different look than what it had previously. Okay. See, the previously it turned out to be this. It was just I0, only one initial intensity of that beam. Though there were two beams, both of them had the same intensity. Now, I have this pattern. Okay. When I1 and I2 are the intensities of the individual waves given by as follows, which I just said just now. Okay. I have just divided it by half so that you have the 2's can cancel out somewhere and they look like decent kind of thing. The half has come from here. Okay. The total intensity I then changes from the maximum value to the minimum value as follows. Okay. Now, okay, this is my intensity. This is my intensity. Okay. So, how does this intensity change when the phase is changing? So, I am only bothered about the change in phase. The change in phase is bringing about a change in my intensity pattern itself. So, at cos delta equal to minus 1, suppose this is minus 1, okay, this is minus 1 and this whole thing turns out to be like this, root of I1 minus root of I2 whole square, that you can see it easily. Okay. So, root of I1 minus root of I2. So, that is the intensity when cos delta is equal to minus 1. Okay. Now, suppose cos delta is equal to plus 1, then it will be root of I1 plus root of I2 whole square. Obviously, there is a plus sign here, this is the maximum intensity that you can get. There is a minus sign here, obviously this is the minimum intensity you can get, because cos delta moves from minus 1 to plus 1 and all others in between. Okay. So, cos delta moves from here. So, the phi can change, the delta can change, that means phi 2 minus phi 1 can change in such a way that cos delta is equal to minus 1 and cos delta is equal to plus 1. Okay. So, now I have two beams, the intensity, they have overlapped with each other, okay. They have crossed each other in space and in time, and they have given rise to a minimum intensity and a maximum intensity. And it is regulated by that phase, which is that cos term. Cos is an undulating term, you know, cos delta. Any cos term is an undulating term. So that means this is changing like this. This is my intensity. Okay? Because of that cos delta term, it is changing like this. And this is my I maximum. And this is my I minimum. Okay. Actually, this I should draw it in a slightly different way, because I minimum is not 0. You know, I minimum has some value, so it's not exactly 0. So I should draw it something like this. Okay. So this is I minimum, which is not exactly 0. But consider the case when both the waves had the same amplitude, or both the waves or both the beams of light started off with the same intensity, okay, which was I0. So then I have to consider this. This is the more generalized case, where the two amplitudes are not the same when we start off, and this is the more specialized case where the two amplitudes were equal. Now suppose you put the value of cos delta equal to -1 here, then this intensity would become 0. Not I0, would become 0. Okay. But when cos delta is equal to +1, then I would become equal to 1 and 1, 2I0. So in this case 1, and this is case 2. Okay. In case 1, your minimum intensity is 0, exactly 0. So it relates to this equation actually, where this is 0. Okay, absolutely 0. I'll put this as 0. Okay. So the I minimum is equal to 0, and the I maximum relates to 2I0. Okay. So maximum and minimum. Okay. So just think about it, when you get a fringe pattern, this is a fringe pattern. Don't you think this will have a sharper fringe pattern picture than this? So on an actual paper or on an actual detector, suppose you are watching this spatial change in flux density or change in the intensity, you know, this will be in case of this. Okay. You will get a fringe pattern like this. On your detector or on a piece of paper, wherever your detector thing. So, you are getting fringes of this kind, and this red part is, say, which I have just drawn it in red, it is 0 intensity. Okay, it is dark, this part is dark, this part is dark, this part is dark, and in between is the maximum intensity. Or you can think of it the other way, in between is the least intensity and the red part is the darkest one. Basically, you are getting fringes like this, and they are very sharp and well defined fringes. Why? Because this part, this white part is absolutely 0, there is no intensity there. Okay, it is absolutely 0. So, these look, it will appear to you as very sharply defined fringes. Okay. Then what about this case 2? In case 2, what will happen is, you will have fringes like this. Okay, these are the maximum intensity. Suppose I am calling this red part the maximum intensity. Okay, and the in between part is dark, dark part, or the minimum intensity. So, the minimum intensity is not 0 absolutely, it has a I minimum, okay, given by this formula, okay, which is not 0. So, here you will get some kind of some light, kind of a light. So, basically what you will get is some sort of a background light is also there, and this fringe pattern sits on top of it. So, obviously this fringe pattern is not as sharp or as well defined as this, because there is some at the minimum part also, it is not 0. So, some sort of a merger of this into this can happen. So, this is more well defined and this is not that well defined, this is sharper and this is not so sharp. Okay. So, in order to get a very sharp pattern of fringes, you should start off with equal amplitude for both the waves. Okay. Now, what I have described till now is two beam interference by amplitude division. I have divided that amplitude are equal. I have divided the amplitude. I am only talking in terms of the amplitude. Everything else is intact. Okay. So, this is two beam interference by amplitude division. So, in my next lecture, I will talk about how to bring about such a amplitude division. Okay.